Hello and welcome to today's lesson where we're going to look at the national grid. Now in today's lesson we're going to try and understand the layout of the national grid, which fits into the electricity topic for AQA GCSE Physics and AQA separate combined science. So it's a module which can be in both the separate science and the combined science. So if we've been successful and learnt in today's lesson, you should be able to understand what the national grid is, understand why we use transformers in the national grid, and understand the relationship between current and length of wire in electrical cables. So it links into the following part of the AQA separate science and combined science specification, which is the national grid, which links into the electricity module for those particular courses. Now we know that electricity is produced in power stations around the country, but many of us do not live near power stations. So how do we get electrical power to our homes? Well, electrical power is transferred from the power stations to the consumers using something we call the national grid. Now, the national grid is a network of transformers, which are devices that change potential difference, and transmission cables that link power stations to consumers. So many students, when they actually have to give a definition of the national grid, forget to mention the transformers section. So don't forget it. You've got to remember the national grid is a network of both transformers and transmission cables. So the national grid, which is the network of transformers, devices that change potential difference, and cables that link power stations to consumers. So what's the actual process of the national grid? Well, stage one, the power station. So after generation at the power station, a step-up transformer increases the potential difference of your electrical power. So remember, a transformer is a device that can change the alternating potential difference and therefore the current of a source of electrical power. So at stage 2, after your step-up transformer, that electrical power then travels through the transmission cables. So it travels at a high potential difference, and the reason for this, which we'll look at in more detail later, is that this allows a current to be very low in the cables, which is important because what happens is current allows energy to be dissipated out of the cable into the surroundings via heat. So if a high potential difference means a low current, less energy will be lost by the particular transmission cables of the national grid. Then stage 3, at the step down transformer, the step down transformer decreases the potential difference to a safe value, so it's safe to use at the home and in buildings such as schools and factories. So let's just have a look at a diagram of the national grid. So you've got here at the start a power station, which is where the electrical power or energy is produced from energy resources. You then got a step up transformer where the potential difference of the power is increased but the current is decreased. At the transmission cables, the electrical power or the electrical energy is transferred through those cables. You then got the step down transformer where the potential difference is decreased and the current is increased of the electrical power. And then finally, the electrical power or the energy is used at homes, at factories, at schools, and transferred into the stores. So a bit more of a clearer look here. You've got your step-up transformer, which is increased the potential difference and decrease in the current. You've got your transmission cables where the electrical power is transferred here, and then at your step-down transformer, the potential difference is decreased and the current is increased. And you've got to remember the approximate potential difference values in each part of the national grid: the step-up transformer, the transmission cable, and the step-down transformer. So just please remember that power stations and homes link into the national grid, but they are not part of the national grid. So the national grid will only consider the transformers and the transmission cables, not the power stations and not the homes. So only the transformer and the cables of the national grid. The homes and the power stations link into it, but are not actually part of it. So why use transformers in the national grid? Well, we use transformers in the national grid as it ensures that electricity and electrical power is transferred efficiently around the country. If we didn't have transformers in the national grid, you would need the high current which is needed to power devices will be quickly dissipated due to high resistances in the transmission cables. So we can explain the need for transformers by looking at what happens in the transmission cables of the national grid. So what you know is that as a current flows through a transmission cable, a resistance will occur and dissipate energy out of the transmission cable. So the resistance causes energy to be lost to the surroundings. Now the higher the current, the faster the electrons are moving, the more collisions with the metal ions, so the higher the resistance. So a high current going through a transmission cable would lead to a high resistance. So lots of energy will be quickly dissipated to the surroundings, and so you have no electrical energy at the output, which is the useful energy output, so the device you have connected wouldn't work very well. So for the national grid to be efficient, less energy needs to be lost to resistance in the transmission cables. So the current in the transition cables needs to be low. Now this can be shown by the equation that power loss equals current squared times by resistance, which is an equation you've seen before. So this is an equation to work out the electrical power dissipated to the surroundings in transmission cables. Remember, dissipate means to transfer not usefully, so spread out the energy into different stores. So the lower the current in the transmission cables, the lower the power loss, as you can see by the equation. So the lower the power loss, the more efficient the energy transfer. So this shows that if we want a very efficient energy transfer, we don't want much energy being dissipated to the internal energy of the surroundings. We've got to put a low current through the transmission cables. And secondly, you might also say, if you lower the resistance in the transmission cables, well then the power loss would also be lower. So to lower the power loss, you would have a more efficient energy transfer. So another way in which you can make your energy transfer more efficient is, as well as having a low current, you would make your transmission cable out of a low resistance material. Now producing a low current in the cable has a greater effect at reducing the power loss in the transmission cables compared to the low resistance, as the current is a squared term in the equation. So you've got two factors of that particular point. So the low current will have double the effect somewhat than the resistance being lower. Now, transformers work on the principle that the power in the national grid is constant, and we use this to lower the current in the cables. So this makes the electricity transfer very, very efficient because little power is lost in the transfer process. Now the overall power in the national grid is constant, and we know that power in the national grid is equal to potential difference times by current. You've seen this before. P equals V times by I. So because power has to be constant throughout, when the potential difference increases, so when V goes up, I, or the current, will have to be smaller to get the same value for power. So this actually gives little power dissipated in the wire because current has decreased, and we know that power dissipation is equal to I squared R. So if I has gone down, power dissipated has gone down, so this ensures the electrical energy transfer is efficient. But if we had the potential difference decrease, the current would increase, which would give us more power dissipated in the wire, because you know P equals I squared R, so if I goes up, power dissipated goes up. However, we do this to make the potential difference safe to use in electrical devices in the home. So the national grid in the United Kingdom was set up in 1926, and then the government decided the electricity would be supplied at 240 volts, but this was lowered to 230 volts in 1994, which is the mains potential difference. So now all devices which are connected to the mains, such as anything in a school or in a factory or in your home, has a potential difference of 230 volts. Now the government decided we would have a national grid to ensure that cities would share electricity at the same potential difference, so electricity can be produced in different power stations but be supplied around the country to where the demand was needed. So let's just clarify what we've learned. At the power station, the electrical energy is originally produced from energy resources. Now the potential difference at the power station is 25,000 volts. The potential difference is then increased after it leaves the power station. That's what the step-up transformer does. So the step-up transformer will increase the potential difference and the current will be decreased. So we say that the potential difference has been stepped up, hence the name step-up transformer. Then, what do we know? That the step-up transformer has raised the potential difference to about 132,000 or 132 kilovolts, so therefore the current has become lower, so therefore less current is needed to transfer the same amount of power, so a lower current passes through those transmission cables, so the energy losses due to the heating effect are reduced to almost zero because the current is such a smaller value, so the power loss due to the current going through the cables is very low, but then we need to lower the potential difference at the end of the grid cables so we can use the mains electricity in our homes, in our schools, in our factories, in our buildings. In addition, remember we said the transmission cables are made from a low resistance material to further reduce the power loss to the internal energy store of the surroundings. So electricity in terms of electrical power and electrical energy is transferred in the cables. Then after the electrical energy or the electrical power reaches the homes and buildings, that it needs the power, then the potential difference is stepped down to 230 volts, so it makes it safe to use in the home. That's what your step down transformer in the national grid does. So the potential difference is decreased and the current is increased. So we say the potential difference has been stepped down. So let's just clarify. In a power station, electricity is generated 25,000 volts. A step-up transformer increases the potential difference to 132,000 volts in the electrical cables. If the cable had a high current, it would dissipate a large amount of electrical power to the surroundings due to resistance. So therefore, to minimize this, we have a high potential difference and a low current. Then a step-down transformer decreases the potential difference to 230 volts, so it's safe to use at home. So let's just once again go over this with a schematic diagram. So the national grid is there to reduce energy loss or power loss in the transfer of electricity around the country. You've got your step-up transformer where the potential difference is increased and the current is decreased. You've got your transmission cables, which is where the electrical power and the energy are transferred. And then the step-down transformer, you've got your potential difference being decreased and your current being increased. So overall, the national grid increases the efficiency of transfer of electricity in the country. Without the national grid, you couldn't have large, useful power outputs in houses, in schools, in factories, in office buildings. It wouldn't be possible without the national grid. So you've got your different parts of the national grid. The step-up transformer, the transmission cables, the step-down transformer. Anything else isn't part of the national grid. So just remember, how does this increase the efficiency? Well, the step-up transformer increases the potential difference and lowers the current to increase efficiency. The transmission cables are made from a low resistance material to increase efficiency, and then the step-down transformer decreases the potential difference and increases the current, so it's safer to use in your devices at home. So the different parts of the national grid all have different functions, but overall the aim of the national grid is to ensure that the useful power output of the national grid is as high as possible, so schools, in buildings, in homes, in factories and offices can all have a high useful power output. So let's just clarify what we've learned in today's lesson. The national grid is a system of cables and transformers linking the power stations to consumers. Electrical power is transferred from the power station to consumers using the national grid. The step-up transformers are used to increase the potential difference from the power station to the transmission cables. Then the step-down transformers are used to decrease to a much lower value the potential difference for domestic use. And then you should be able to explain why the national grid is an efficient way to transfer energy. So if you've been successful and learned in today's lesson, you can understand what the national grid is, understand why we have transformers in the national grid, and understand the relationship between current and the length of wire in electrical cables found in the national grid. So thank you very, very much for listening to today's lesson, which is a lesson on the national grid, which is found in the separate science and the combined science module of electricity in GCSE physics. Thank you and have a lovely day.